everybody. Today I would like to speak about PID control, proportional, integral, and derivative, and we will have application example about how we can use PID control for a control loop.
Modulating control. In modulating control, the feedback controller operates in two steps. First, it computes the error between the controlled variable, the process feedback, and the set point. Then it produces an output signal to the control valve to reduce the measured error to zero. This type of control, operating with continuously changing analog values, includes three basic modes: proportional, integral, and derivative. Most modern controllers include the three PID functions. However, loop operation and tuning parameters may only activate a single mode, a combination of two modes, or a combination of all three modes. PID control. The PID control scheme is named after its three correcting terms, whose sum constitutes the manipulated variable, MV. The proportional, integral, and derivative terms are summed to calculate the output of the PID controller. Defining as the controller output, the final form of the PID algorithm is where Kp is the proportional gain, a tuning parameter. Ki is the integral gain, a tuning parameter. Kd is the derivative gain, a tuning parameter. T equal Sp minus Pv, T is the error, Sp is the set point, and Pv, T, is the process variable, T is the time or instantaneous time, the present. Tau is the variable of integration, takes on values from time 0 to the present t. Proportional term. The proportional term produces an output value that is proportional to the current error value. The proportional response can be adjusted by multiplying the error by a constant Kp, called the proportional gain constant. The proportional term is given by a high proportional gain results in a large change in the output for a given change in the error. If the proportional gain is too high, the system can become unstable. In contrast, a small gain results in a small output response to a large input error, and a less responsive or less sensitive controller. If the proportional gain is too low, the control action may be too small when responding to system disturbances. Tuning theory and industrial practice indicate that the proportional term should contribute the bulk of the output change. Integral term. The contribution from the integral term is proportional to both the magnitude of the error and the duration of the error. The integral in a PID controller is the sum of the instantaneous error over time and gives the accumulated offset that should have been corrected previously. The accumulated error is then multiplied by the integral gain, Ki, and added to the controller output. The integral term is given by the integral term accelerates the movement of the process toward setpoint and eliminates the residual steady-state error that occurs with a pure proportional controller. However, since the integral term responds to accumulated errors from the past, it can cause the present value to overshoot the setpoint value. Derivative term. The derivative of the process error is calculated by determining the slope of the error over time and multiplying this rate of change by the derivative gain Kd. The magnitude of the contribution of the derivative term to the overall control action is termed the derivative gain, Kd. The derivative term is given by derivative action predicts system behavior and thus improves settling time and stability of the system. An ideal derivative is not causal, so that implementations of PID controllers include an additional low-pass filtering for the derivative term to limit the high-frequency gain and noise. Derivative action is seldom used in practice though, by one estimate in only 25% of deployed controllers because of its variable impact on system stability in real-world applications. Application example with feedback PID controller, water flow control. In an industrial plant, since there are many factors that we need to consider, We need a robust controller that takes our parameters into account and does hundreds of calculations to determine where the process is and where it needs to go. Let's say that we need to control water flow through a pipe. The set point of water flow is calculated based on calculation. We will control this flow based on a modulating valve. In this case, the more open the valve, the more water allowed to flow. The requested position of the valve is our control variable. Downstream of this modulating valve, we have a flow meter that will measure the water flowing through the pipe. This is our feedback or our process variable in order to control this process. Our PID controller will be able to use the parameters we specify to determine the controller's reaction to our process. If you like this video, please subscribe this channel and press bell icon to get notification of new videos. Thank you so much for watching and have a nice day.